Okay, thank you for the introduction. My name is Anasuya, and I'll be talking about maliciously secure MPC protocols in this model called the scales model. This is joint work with my PhD advisor, Karmi, and our collaborators, Zach from Georgia Tech and Manoj from IIT Bombay. And this is a follow-up talk from one that I gave in TPMPC 2 years ago. So, yeah, in case people remember. Okay, so let's first briefly go over the model. We all know that MPC basically involves multiple parties with their private inputs that want to compute a function on these inputs, and they do so by communicating in such a way that nothing beyond the function output is revealed. And now what happens when these parties don't have enough compute power for this? Well, there are protocols that allow you to outsource all the computation to these to special parties called servers that do not have any inputs, but they just sit around and help out with the computation. And this is what we call a API service. And today, with the blockchain boom, we have this huge set of servers already out there, sitting there, doing something else that are ready to use. And now, which brings us to the question of how can we best leverage this already present resource to give us MPC as a service. And this is great, so it's already there, but there is this one caveat that comes with it, which is that this big server pool also comes with a very big, a very powerful adversity that can corrupt a set fraction of the entire pool. This may be like 1/3 of the pool, half of the pool, even more. So the question is, in this case, now we have these clients and you need to, and they have inputs and they need to outsource their computation to the server pool. How do we do that off? Typically, how it happens is that these clients, they create one message which somehow secretly encodes their inputs and they put it out there, give it to the servers. Then the servers, for multiple rounds, talk to each other, do some computation, and in the end, they produce one message that they give back to the clients, which the clients can now use to locally decode the outputs. Now, this is great, but there are just too many servers, and if you need all of them to start working on your MPC protocol, it's very inefficient, computation-wise, communication-wise. So, ideally, what we would want is that clients send a message, and then a very small subset of this entire pool come together and they participate in the computation. And this is very efficient because only they need to talk to each other and then send a message back. So, however, this becomes a problem if our adversary is an adaptive adversary. So, in this case, what happens is the adversary can corrupt parties after knowing who are participating in the computation. And this subset of parties is like very small, and the adversary has enough power to corrupt all of them. So, and when all the parties participating in the computation are corrupt, then all the inputs are compromised, and this is bad for us. And so, the real question here is how do we address this efficiency versus adaptive corruption issue. And one way that this has been done in literature is through ephemeral servers. And this was introduced in previous work as the YOSO model, short for you only speak once. And the sort of philosophy here is that when the computation servers are chosen and to compute, nobody else knows that they are the ones who are computing. They compute silently, and then only when they post or they send out a message is when everybody, adversary included, knows that, oh, these were the parties that were actually computing. And after they post that one message, they won't participate in the protocol. So at that point, if the adversary comes and corrupts them, whatever, right? It doesn't harm the protocol. So that's what we want. And now today, what we'll be talking about is this variant of the YOSO model called the scales model, and this is a model that admits better protocols in the dishonest majority server pool setting. So Here's a brief outline of what we will cover. We'll first look at what the scales model is and what a scales protocol looks like. Then we will start constructing a semi-honest secure scales protocol, and towards that we'll first look at one major building block that we're going to use throughout, and that is random learning. And once we have a semi-honest scales protocol, the last part of the talk will talk about how to take this particular protocol and lift it to malicious security. And that's it. So let's get started. So the scales model. Scales literally stands for small clients and large ephemeral servers. And as the name suggests, we have small clients that have very small inputs. They do very little computation. These clients do computation proportional to their own input size only, and some constants and the security parameters, and that's it. In particular, their computation is independent of the size of the entire function space, and also the size of the total input. How many other clients are there, and so on. So that is, and these clients, they post maybe 2 or 3 messages, and they need to, and these clients need to maintain state between their messages. Okay, so that was the clients. Then we have the server pool. The servers, when they participate in the computation, if they do, they need to do a word proportional to the function size. And they only need to speak once. Now, a scales protocol operates over a bulletin board. So all communication is happening over the bulletin board. There is no point-to-point channel between anybody, and it proceeds in phases, so like maybe 2 or 3 phases. And how it works is that in each phase, first all the clients come up and post one message each, and to start the phase. Then one server gets secretly elected. For multiple rounds, each round one server gets elected. At that point, only that server knows that it's going to be part of the computation. Then it reads stuff from the bulletin board, it silently computes what it needs to send. Then, before it is ready to send its message, it will first erase its state of the protocol, and then it will post a message. And at this point, if this server was initially honest, its identity is revealed to the adversary, and the adversary can now look at it and corrupt it almost instantly. However, its role in the protocol is done, and it has erased its state, so it doesn't really help the adversary much. So now, and the next round, another server comes up and does exactly the same thing until we're happy with the number of servers we have in this particular phase. Then we start the next phase where we have, again, a set of client messages and one by one a set of server messages. And such a protocol needs to be secure in the presence of an adversary that corrupts an arbitrary number of clients and all but one server in each phase. So that's what we have here. Now this begs the question of how many servers do we need in each phase? Well, that really depends on how the corruption ratio in the server pool. So for instance, let's say if a fifth of the server pool was honest, then 1 in 5 servers in expectation would be honest on random election, right? So say 10 servers. So we have like a constant number of servers that are going to participate, and this is the protocol. I mean, this is how the protocol works. Now, this automatically gives us 2 things. One is we can see that these protocols work very well in dishonest majority server pool settings. And the other is that we have constant number of rounds. Because constant number of phases, constant number of rounds in each phase, and that. So that's that. Okay, so now let's look at the semi-honest secure scales protocol. Before we go into what the protocol is, we'll briefly look at the major building block that we're using over here, and it's called randomizable guarding. And before we look at what randomizable guarding is, let's just briefly look at what guardable circuits are. I know we did this yesterday, a lot of people talked about this. So this is a setting in which you have a guardrail and an evaluator. And so for a function f with such binary inputs, the guarder has this guarding algorithm that can take the function and use some randomness to create a guarding circuit. And it also creates a set of labels where there is, for each input bit position, there is a pair of labels, a 0 label and 1 label. Now, if you take one label from each edge to represent an input, and you take the guarded circuit and you give it to an evaluator, this has this other function, the evaluation algorithm, that can take the function output. And the guarding and the labels are such that nothing beyond the function output is read. So this was plain guarding. You have one guarder and this is a local operation, but now what happens in multi-party settings when you need all the code security? Typically we need all the parties to be participating in guarding together. Now, yes, this is not something new and distributed guarding exists. But distributed guarding is a lot of like back and forth, a lot of communication, everybody needs to talk to everyone. And this is something that our communication pattern kind of doesn't support. So that is why we need a way to sort of serialize the distributed guarding process. And we do this by using re-randomizable guarding. This adds this extra role to the guarding process, and this role is that of the re-randomizer. The re-randomizer can take a guarded circuit, add extra randomness to it, and create a re-randomized guarded circuit. This already, this still is a guarding of the same function S, and now it also outputs some extra information that can turn the labels of the old guarding into labels compatible with the new guarding. And then the evaluator, when it gets this new guarding, new labels, it can only get the function output. We also need one extra property over here, which is if we have this semi-honest adversity that corrupts the guarder and the evaluator, so note that it has all the randomness that went into creating the original guarded circuit. Then, even then, this re-randomized guarding needs to look no different from a fresh guarding. So that's what we need. So this is our DCs. Now let's look at, so this already gives us like a framework for how we would create a semi-honest stage protocol. And the idea is that, well, guarding, re-randomizing, evaluating, they're all like function size dependent tasks. So let's make the servers do everything. And okay, so semi-honest protocol, we have two phases. The first phase we guard the circuit, the second phase we evaluate the guarding. So first, the clients come up and they encode their inputs and they put it on the bulletin board. How does this happen? Well, we won't go into the details of this, but we use a two-round OT in a very special way, and and that's about it. And this is like the OT receiver's message. So then the first server is the guarder, and it takes the function, it creates the guarded circuit. Then out of all the labels, it creates the OT sender messages and it posts the guarded circuit and OT sender's messages on the bulletin board. Then every other server takes the guarded circuit just posted, the one previous, it re-randomizes it. Then it takes the OT sender message just before and it updates the labels within it to match the labels of the new guard. And these are posted. And once enough servers do this, that ends the first phase. Then in the second phase, what happens is, the clients come up, they only read the last message, the OT message of the last server, and only the one that was addressed to them. And then they decode their label corresponding to the last guarded circuit, and they put it on the board. And then one server comes up and evaluates the guarding, and that's it. You have the function off. So this is the semi-honest secure protocol, and it's easy to see why this is secure when you have an adversary that you have, any number of clients, all but one guarder and re-randomizers, and even the evaluator. So this is the protocol. So now all that remains is to see how we can take this and get malicious security out of this. So we just, and since we're in the dishonest majority setting, the best we can do is move forward security with the board. Okay, how do we do this? Recall that we used two things in our protocol. We had an OT protocol and we had a gardening object. So first thing, very obvious, take the OT protocol, convert semi-honest to malicious security. And it kind of already, we are already stuck. Because, well, you don't have malicious secure two-round OT in the plain model. So we need to use either a random model or a CRS. And since we need our OT to sort of be updatable and it needs a particular structure, we just use the CRS-based OT. Random model doesn't give us that structure. So that is that. Now, and the second thing we need to do is, well, the servers that are gardening and randomizing, they need to prove that they did their jobs correctly. And because the protocol is only secure if the gardening and randomizing was done semi-honestly. So, and how do we do this? Well, there is already a machinery for this existing, and one way very obvious to do this is using snarks. Okay, so I am a server, I did my gardening or my randomizing, then I prove in zero knowledge that I did this job correctly. And this is neat because this needs setup, yes, you already have setup. And we create this one very tiny proof which everybody can publicly verify and we're done. However, there is one big problem with this, and that is, yes, correctness of gardening and randomizing is an NP statement, but it's a very big NP statement. And we don't want to be, and this is a very expensive computation. So the question over here really is, can we do any better? And the answer is, well, yes, we can. And that's what we do. We create zero knowledge proofs that are black box in the randomizing gardening. This basically takes advantage of the homomorphic properties in the randomizing gardening and gives us a very simple proof that reduces prover computation. And so there are a lot of details that are hiding over here, but here's the overall here's like the overall design of the proof. So here's for example, we first look at the proof of correct gardening, and this is going to be a Sigma protocol. So there is a prover, a verifier, there are discrete messages, and this is roughly how the discrete log Sigma protocol works. So recall that you had, in what happened in discrete log, you have the prover creates a first message using some randomness, right? And the verifier samples a bit, and if the bit is 0, it will only show that it made its first message correctly. If the bit is 1, it will use the randomness to somehow mask the discrete log witness, and you can obviously check something. And the argument is if both of them are correct, you have the correct proof. So similarly over here, we have the prover has some randomness for which it has to prove that the garden circuit is the correct gardening of the function f. Now, the first method is it takes the garden circuit, it samples more randomness and it randomizes it. And this RBC is given to the verifier. Then the verifier takes a bit, and if the bit is 0, it needs to show that the RBC was correctly randomized from the DC. And if it is 1, it has to show that the RBC is the correct gardening of the function f. So this requires somehow composing this randomness R prime and R. And this is possible. I won't go into the details of how this is done, but yeah. So this is the Sigma protocol, and if we use this as it is with a semi-honest protocol, this gives us a covert secure protocol. It just doubles the semi-honest costs. But if we want to use it for malicious security, we need to amplify soundness using parallel verification. So I mean, if you need 2 to the power negative S soundness error, you need like S times the semi-honest cost. So that's what's happening over here. And there are other details that I'm not talking about, like how do we ensure compatibility with OT labels, but this is a better paper for it, and we don't have that. So, yeah. And there's one last thing that we need to make this work and it'll be done. And that is, we need the prover to speak once. The prover is the server. And Sigma protocols make the proof space twice. So one obvious way of doing it is well peer checking. You have a random oracle, you take the 3-message protocol, and you turn it into one message as a true versus the verifier, and it's publicly verified. But, well, we don't want to use it because, well, we're already using the CRS, so why add more heavy machinery? And so the second thing that we come up with is this, well, different kind of OT. We define it as a structure. It's called distributed commuted index oblivious transfer. And what it does is it lets multiple choosers pick a random joint bit collectively. So they pick one bit at random, and then the verifier and the sender has 2 messages, and only one of these 2 is revealed. Which one is revealed corresponds to the XOR of all the choices. And so here's how it happens. So the protocol typically works in which, so there's the first message that the receivers all send, then the sender creates its second message, and that is a function of its inputs, and then the receivers post some public outputs, and this allows you to publicly reconstruct the sender's message. And you can kind of see why this can be used to streamline our Sigma protocol, right? Because all that happens is that the first, so the prover can create the first Sigma protocol message and both the third Sigma protocol messages and put them into the OT and done. So this is something that we call ephemeral prover zero knowledge and EPZK. And this is it, and now we're ready to look at our malicious secure protocol. We have 3 phases, and the first phase is the encoding phase. You have the clients, they impose a message, this is the OT receiver message for their inputs and their contribution to the zero knowledge challenge. Then the first server guards the circuit, creates the OT sender message with the labels, it creates the proof message and posts all of this. Every other server re-randomizes the previous target, updates the OT message, creates their proof message and posts this. Encoding that. Now you have the verification phase. Over here, the clients come up and they post what is required to complete the zero knowledge. Then, one by one, a bunch of servers come up. They check all the proofs of everybody in the encoding phase and post either accept or reject. And if everybody accepts, then in the decoding phase, the clients come up and post the labels to evaluate the last gardening. Then one by one, a bunch of servers evaluate the gardening and post the output. And the client believes them with all the output services. And that's it. This is the protocol, and this is secure when you have an adaptive adversary that develops all but one client and all but one server in each phase. So to conclude, we have all our building blocks that we saw can be built using DDH, and we have maliciously secure scale protocols. We saw 2 ways of pulling this off. One was using the information read transform, that uses the CRF and random oracle, and the other was the protocol that we just saw that had the client speak twice. The random oracle protocol needed the client to speak twice. So, and both these protocols are secure, and that's basically it. So here are certain open problems. One of them is that we still don't know how to make scales protocols that are guaranteed of good delivery. And I mean, for instance, even this protocol in the honest majority server pool setting will still give you security to the board. So if there is that, then there is, we don't know how to make scales without CRS yet. So if you can make one in a random oracle model or a decaying model, that would really help. And yeah, so if you can use scales from other hard assumptions, that would be cool too. So that's it. All our papers are on eTrade, and that's all I have. Thank you.